Welcome to absorption of light. So, when a photon is absorbed by a molecule, then the energy of the molecule increases because that energy of the photon has to go somewhere. The molecule has been promoted to an excited state, and the ground state is the lowest possible energy state of the molecule. So the molecule may have already existed in the ground state, it may have existed in one of the excited states, and now it's moved up to a higher excited state. So, if we have down here our ground state of our molecule, that molecule may absorb some energy and move up into one of the excited states up here. And then later on, it can emit some light and transition back down to the ground state. Absorbance of microwave radiation generally stimulates rotations in molecules. Absorbance of infrared radiation generally stimulates vibrations in molecules. Absorbance of visible and ultraviolet radiation generally stimulates electrons to transition to move to higher energy levels within molecules. And absorbance of shortwave ultraviolet and X-ray radiation generally breaks chemical bonds and ionizes molecules because there's so much energy involved in those photons. So yes, medical X-rays are in fact damaging your body. They're ionizing radiation. These are damaging to us. This is why ultraviolet light causes skin cancer, because it's damaging your DNA. So with the medical X-rays, they're useful, so we use them sparingly because they can harm us, but we do use them because they're very useful to us in diagnosing certain ailments, but we do shield as much of your body as possible using lead, generally lead vests. So when a sample absorbs light, the irradiance of the beam of light decreases because we've pulled some energy out of that electromagnetic radiation. So the irradiance P is the energy per second per unit area of the light beam. So as a molecule absorbs some light, that molecule has removed some energy from that light beam. So here we have a rudimentary spectrophotometric experiment. We have a light source, we have a monochromator or wavelength selector, we've got our sample here, and we have some detector that detects the light passing through. So light from our light source comes out of the light source, and it's multi-wavelength. We have a broad spectrum of light coming out of the source. It goes into a wavelength selector that picks a wavelength. This is called a monochromator. So this is selecting ideally one wavelength, although generally it's a small wavelength range. And a monochromator could be a prism, so you know that a prism takes in white light and it spreads it out, and if you shine the light on, say, a screen, you'll see a rainbow pattern. So it may be a prism, a diffraction grating, or maybe a filter. Then that light that's coming out of the monochromator is composed of just a very narrow range of wavelengths. And this is now called monochromatic. So mono meaning one, chromatic meaning color. So this is one color of light coming out and hitting our sample. So the monochromatic light has some irradiance that we're going to call P0, P0. This hits the sample. The sample is some length long, B. The light beam then leaves the other side of the sample after traveling that distance B, and now it's got some other irradiance P. So some light might be absorbed by the sample, and this means that P, this value here, is less than or equal to the amount of light going in, P0. So the fraction of light that passes through the sample is then the transmittance, which we symbolize with a capital T. So transmittance is equal to the amount of light coming out of the sample divided by the amount of light going into the sample. And T is somewhere between 0 and 1 because it's a fraction, and percent transmittance is then 100 times the transmittance. And then the percent transmittance is somewhere between 0 and 100%. The absorbance, A, is defined as A equals log of the ratio between the light coming into the sample and the light going out, which is minus log of the transmittance. So if no light is absorbed, then the irradiance of light coming out of the sample is equal to the irradiance of light going into the sample, and then the absorbance is equal to a log of 1, which is 0. Now if 90% of the light is absorbed, then 10% is transmitted, and the amount of light coming out is 1/10 of the amount of light going in, and then the absorbance is the log of 10, which is 1. If 99% of the light is absorbed, then only 1% is transmitted, and P is 1/100th of P0, And that means the absorbance is the log of 100, and that means that the absorbance has a value of 2. So note that absorbance is sometimes called optical density, and the absorbance is directly proportional to the concentration C of the light-absorbing species in the sample. And so this is called the Beer-Lambert law, or Beer's law. So absorbance is equal to epsilon BC, where epsilon is the molar absorptivity of that light-absorbing species, B is the path length, and C is the concentration. So this law, the Beer-Lambert law, or Beer's law, is the key to spectrophotometry as applied to analytical chemistry, because we're interested in finding concentrations of our analyte, and we have to have Beer's law apply in order to be determining the concentration. So know that absorbance then is dimensionless, but you might see it written with absorbance units after the number, and the concentration is generally given in molarity. The path length B is generally given in centimeters, and usually the path length is 1 centimeter, although you could have other cuvettes as well. The epsilon there is the molar absorptivity, also called the extinction coefficient in older texts, and has units of per molar per centimeter. So the molar absorptivity describes how much light is absorbed at the wavelength of interest, and it changes with wavelength, so this is wavelength specific. Note that we could have written Beer's law like this, where we say the absorbance at some wavelength is equal to the molar absorptivity at that wavelength times the path length times the concentration, because both the absorbance and the molar absorptivity depend upon the wavelength. And an absorption spectrum is a graph showing how A, or epsilon, really varies with wavelength. And note that the plural form of spectrum is spectra. So that portion of a molecule that absorbs light is called a chromophore, and any substance that absorbs visible light will appear colored when white light is transmitted through it or reflected from it. And remember that white light contains all the colors of the spectrum. Now, the substance absorbs certain wavelengths out of the white light, and our eyes detect the remaining wavelengths, which means that we see the complement of the color that is absorbed. For example, bromophenol blue absorbs orange light, so we see the complementary color, which is blue, hence the name. Beer's law works very well for dilute solutions, which means less than or equal to 0.01 molar. But at higher concentrations, the solute molecules are much closer together, and then they interact with one another. And when they interact, some properties, including molar absorptivity, can change. So sometimes a light-absorbing molecule may interact with solvent or another solute, even if the other molecule does not absorb at the wavelength of interest. If the absorbing molecule participates in an equilibrium reaction, then the molar absorptivity may change with concentration. For example, the weak acid HA dissociates into hydrogen ions and A- ions. This is our conjugate base. And so we have our equilibrium here. HA dissociates into H plus A-. And at high concentration, the acid exists mostly in the undissociated form. It exists mostly as HA. But at low concentration, then the acid exists mostly in the dissociated form. So it exists mostly as that conjugate base. So if A-, if the conjugate base does not have the same molar absorptivity as our protonated form, then the molar absorptivity will change with concentration, and the solution will appear not to obey Beer's law as it's diluted. So that was the absorption of light.